Good morning to all of you, and welcome back on the training sessions. Yeah, I know last week it was a rather tough because there was a lot of information, a lot of sessions. From this week on, we will continue the sessions, but it will be mostly one in the morning, one in the afternoon. This morning, we will first start again with a more general training. It will be given by Gilles, and it will be dealing with interpretation of data with respect to plant uptake. And this afternoon, we will have the first session of the analytical part. So you will take on your virtual lab coat, and we will have a session on the determination of PAH. But first, the session of this morning, as I said, will be related to plant uptake. So Gilles, if you can open your presentation, and the floor is yours.
Thank you. Just trying to share my screen.
Yeah, I will wait a second to see how the blocks are on your screen to see if everything is visible.
So, no, not that one. Not the good one.
No.
Yeah, that one. Oh.
It's Monday morning, Gilles.
Yeah, for my computer too. So, share. Diaporama. Okay.
Okay, only on the top. Yeah, if you can move it a little bit more up, the
I
upper.
think it will go automatically.
Yeah, because you're now in presentation mode. It's just yeah, that's great.
Okay.
That's working. Okay, good luck. Thank you.
Okay. So this morning we'll speak about the parameters of soil fertility. I will begin with some concepts. Then we will speak about the plant requirement, about the behavior of major nutrients in soils, and about soil fertility evaluation schemes, such as the one we use in Belgium. And I think it's general concepts that are used everywhere. So about the concept, just to remind that speak about soil fertility. It's one of the major soil ecosystemic services or soil functions that are recognized to the soil. And it's one specific, which will be the provision of food, fiber, and fuel. And this will be the topic that we will speak about today. In this general view, I like it because it shows well that when you are speaking, whatever the framework that you are taking when you speak about soil, here it's the major soil ecosystemic services. At the end, if you want to quantify these functions, services, and so on, you will need to measure soil properties, and there are some that have been recognized for a long time as minimum data sets to measure in order to be able to interpret the functioning of soil, which are the soil organic carbon, the texture, the soil pH, and so on. So these are already well-known parameters that have been studied for long. In the recent years, there's been a lot of talk about soil health, which is a concept which is under a lot of discussions. It's not so new because it has been introduced in the 90s by researchers such as Doran, Parkin, and so on. And it has been defined as the capacity of a living soil to function within natural or managed ecosystem boundaries, to sustain plant and animal productivity, maintain or enhance water and air quality, and promote plant and human health. So it was by Doran et al. In 1996. And so soil health was aimed to be a little bit different as soil quality, which was a composite of physical, chemical, biological properties that provide a medium for plant growth and biological activities, regulate and partition water flow and storage in the environment, and serve as an environmental buffer in the formation and destruction of environmentally hazardous compounds. So soil health is really viewed now as a more general framework as soil quality or soil fertilities, soil function for biomass production. But the main remark that can be done to the soil health is that you don't know really how to differentiate it from soil quality when you have to measure it. And there was another citation from Bouma and Bavey is if we embrace the soil health concept, we better make sure that we can measure it, like we now routinely measure the quality of air, of water, air, nature, and biodiversity. So 30 years of or more of soil quality research has not resulted in an operational measurement methodology. We simply cannot afford the same failure for soil health. So it's a big challenge now if you want to speak about soil health rather than soil fertility, because you want to embrace more functions or to embrace the biological aspects of soil fertility. It's become difficult to measure. And I took this image from the FAO site. Soils, if you cannot measure it, you cannot manage it. And I think it's very important. So soil fertility is a bit, has been studied for a very long time. And it is now defined as the ability to sustain plant growth by providing essential plant nutrients and favorable chemical, physical, and biological characteristics. So it encompasses the three major aspects of physical properties, chemical properties, and biological properties. So when we have a field here, it's a wheat field in southern Belgium. The question is, how do we evaluate the productive capacity of this field? And there's been a lot of work done and in the 70s, I think it was this general framework from the FAO. It was that if you want to make land assessment, you have on the one side the plant requirement or the crop requirement. On the other side, the soil characteristics, what the soil can offer, and you put all both aspects into balance, and it will give you indications about the management practices that are necessary in order to meet these two aspects. So let's begin with the plant requirement. And the first question is, what does a plant need? If you look at the factors of soil fertility, the plant needs light, needs carbon that they will take the plants will take that from the atmosphere. They need temperature. We use the index of the sum of temperature as a indicator of the capacity of the plant to grow. They also need oxygen, hydrogen. They will take from the water, and probably they need much love to grow. That's why you speak to your plant in your apartment or in your house. But we will mainly focus on the other factors of fertility, those that are linked with the soil. And if you look at this image, you see that one of the major aspects is the soil physical habitat of the plant. The plant must be able to investigate the soil with the roots in order to find water. So and so the climatic aspect is important. How much rain is going to the soil, but also the soil structure, as what is the part of the water that will infiltrate in the soil. So the structure at the surface is an important point. And of course, the volume of soil that is available for the root development and the soil structure, it will all determine the quantity of water that can be prospected by and used by the plant. So there is a parameter that is called the exploitable depth. And so that's an important characteristic for the plant development. So they need enough space, they need enough water and enough oxygen in this environment. Then you have other properties, which are the chemical aspect, and it will be how much nutrients the soil can give to the plant. And so the minerals, the quantity and the quality of the minerals will be a part of the total reserve in nutrients that can be accessible to the plant. One important parameters will be the soil reaction, which is measured by the acidity, pH. This is an important properties that governs the other properties. And also another important part is the content of organic matter, which is also a source of nutrient, and the liberation of the nutrients from the organic matter depends on the biological act. But the organic matter is also another important properties for other properties, such as the structure, the resistance of the structure, and so on. So there are many factors of soil fertility. We, in a previous project, we wanted to make an assessment of the ecosystemic services that urban soils could deliver. And we began service by service, and this is the kind of structure that we had for the service of production of food biomass. See that you can have a lot of parameters that can be measured, some for soil quality, some for the environment. And regarding quality, you will have the physical, the biological, and the chemical properties. Regarding the physical, you will look at the structure and the water regime. So you see a lot of properties that can be measured. Also for the chemical, you see a very huge amount of soil properties. And regarding the biological, we have the organic status and the indicators of biological activities. So that was an ideal scheme of food biomass production. But often you don't have access to all the parameters, and so you need to define a minimum data set, which is the minimum number of parameters that you need to in order to be able to interpret. And they are circled here in red. So it's the natural drainage in our system because we have a detailed soil map. It's the texture because we have a detailed soil map that gives indications. This is the pH because it is one of the most important properties. It is the cationic exchange capacity. It's also important properties, and it is the organic status with the carbon and the C over N ratio. So outside, if you don't look at the climatic requirements, the major factors of soil fertility will be the water needs, the nutrient needs, and other limitations such as the sensitivity or the tolerance to various kinds of stresses. Looking at the water needs, I won't go into detail. It's not the focus of the soil fertility. We will mainly be on the chemical characteristics, but if you are interested, there are already tools that exist, and you have the aqua crop from the FAO that can be found, and I think is easy to use regarding other models of fertility. So if you want to incorporate the water needs, there exist some tools that can help, and maybe help you to define the irrigations that are needed for the crop. But also plants need nutrients, and the nutrient needs can be seen as a global needs for all the crop growing at the end of when you are harvesting the crops. See, okay, my crop needed given quantity of NPK, Mg, and so on. But also, it is important to know the stages of development of the crops. And here you have a representation of the potato development. And if you look at the curves of nutrient acquisition, this is cumulative uptake, you see that it's not a straight line. It means that during the development, the plant is taking nutrients at different rates, and it depends on their needs. So the needs are not a mean needs. It's some things that can evolve through the time. And what is important is that they find the nutrients when they need it. And so in modeling or in fertility practices, sometimes you can fractionate the quantity of elements that you give. It's mostly the case for nitrogen. And so it means that some models that exist on the market can have different kinds of modules for the crop growth. This is an example of the sticks model. So they try to modelize the evolution of the crops, and they need some input data such as climate, management, itinerary, the plant and the crop and the soil. And they have relationship between different modules. One is how the crop is growing and what it needs, making links with water balance. So it's very important that will modulate the capacity of the plant to grow, and also nutrient module. Usually it's mainly nitrogen that is taken into consideration. Sometimes phosphorus, but it's seldom with the other elements. And the output are the yield, the stresses, and so on. If we look at the elements, I took this infography from FAO that I like it very much too, because it takes into consideration all the soil nutrients. So they are defined as macronutrients and micronutrients. The definition can change for different classification, if you take some different readings, sometimes you will not have exactly the same list of macro and micronutrients, but here you have a list of effects that are given by these nutrients on the growth and the formation of the crop. You see that there are a lot of elements. Some will promote plant growth, such as nitrogen, calcium, copper, iron, zinc, phosphorus. Others can have are involved in the photosynthesis. Others will increase the disease resistances, reduce the plant transpiration, stimulates microbial activity, enhance the maturity of the grains, favor the quality of the fruit, and so on. So you see that the elements are involved in all the processes of the plant development and all the processes that make yield of good quality. In this system, in the FAO, there are 18 nutrients that are recognized as necessary for the plant growth and the human health. And I think for the plant, it's more 15 or 16 than 18. And so these elements are here classified as macronutrients. So you will find the phosphorus, potassium, nitrogen on the one side, and the micronutrients, so the elements linked to the soil. Of course, you also have carbon, oxygen, and hydrogen, but they are not taken from the soil. And so the micronutrients here are recognized as needed by the plant. So you will find some that we also we also classify in other system as major, such as calcium, magnesium, some sulfur, and others that are always linked to micronutrients such as iron, copper, zinc, and so on. And so there is an important concept in the plant need. It's the concept of essentiality. So what makes an element essential? There was definition conditions that were cited by Benton Jones in his book about plant nutrition and soil fertility manual. It's a good synthesis that I recommend to read, and I used some of the tables from there. The three elements that make a plant an element essential for a plant is that the omission of the element result in abnormal growth, failure to complete life cycle, or premature death of the plant. So if the element is not there, the plant cannot grow well. Also, the element is specific and cannot be replaceable by another. And the element must exert its effect directly on growth or metabolism and not indirect effects such as antagonism to an element present at toxic level. So these are the three characteristics that make element essential for the plant. And about the characteristics of the plant, of the elements in the plant. So again, a table here which will classify them. So you have hydrogen, carbon, oxygen that are taken from the water or from the air. And the one that are taken from the soil are nitrogen, potassium, calcium, magnesium, phosphorus, and sulfur. So I told you it was a different kind of classification if you compare with the FAO, but it doesn't matter. If you look at the range of composition in the plant, see that you have ranges that are from 0.5% to 5% for the nitrogen and the potassium, a little bit wider for the calcium, more narrow for the magnesium, phosphorus, and sulfur. So they are needed in less concentrations than nitrogen, potassium. And about the micronutrient here, we don't speak about the percentage, but more about ppm. So these are the ranges of concentration that you will find in the plant. So chlorine from 100 to 10,000. So it's a very wide range of concentration. Boron, it's less than 100. Iron, it's between 50 and 1,000 ppm. The manganese, the zinc, the copper, and the molybdenum are at concentration usually lower. So if you recognize that these elements are essentials, they must have some functions. So you will find in the PowerPoint the major functions. We will not read them one by one, but it's just if you want to go further, I suggest you to go into the readings of Benton Jones or other good books that exist in the literature. So the nitrogens, the major points related to this essentiality is that they are found both in inorganic or organic forms in the plant. So the nitrogen can be part of the organic structure, or it can be found as a nitrate, nitrite, ammonium in the cells or in the water inside the apoplasm. So it combines with CHO, sometimes with sulfur to form amino acids, amino enzymes, chlorophyll, alkaloids, and purine base. So you will find nitrogen in a lot of molecules in the plants. The inorganic nitrogen, it's in stems and conductive tissues under nitrate form mainly. Regarding phosphorus, it's also very important. It's why it's major or macronutrient. You will find them in the adenosine triphosphate molecules, which is really important regarding the exchange of energy, the energy transfers in the various processes of element uptake, the active uptake by the cells. Also, of course, in the RNA and DNA and other molecules such as the phytin. The potassium is involved mainly in maintaining the water status of the plant. So that's the concentration of potassium that gives the vigor of the plant and makes the water go into the cells and maintain kind of internal pressure. And so it's a very important elements regarding that aspect. And also has a major role in the accumulation and translocation of carbohydrates in the cells. Regarding the other elements, you have calcium, which also play important role in the cell integrity and the permeability of the membranes. It activates enzymes for the division of the cells, so mitosis and elongations. Also, it can have important role in order to detoxify the presence of heavy metals in the plant by binding to them, making binds with some of them. Magnesium is important because it's a component of the chlorophyll. Most plants need to make photosynthesis, and so chlorophyll is the most important molecule for them. It's also a cofactor in most enzymes that are linked to the phosphorylation processes. And finally, sulfur is all involved in the protein synthesis, and it's part of a lot of amino acids and thiamine. So it's a very important, and it will be very important also for the group of Cruciferae and Liliaceae families that because they are a part of the glucoside components. So sulfur can help to reduce the incidence of disease in many plants. So that were the functions of the major or macronutrient. Then you have the micronutrient. I will go a little bit fast there. The one that I believe are the boron, the chlorine, the copper, the zinc, the iron, and the manganese. And usually they are involved in the exchanges of element in the activation of the photosynthetic processes. They are linked to the metabolism of nitrogen fixations and so on. So they have very specific role. They are needed at low concentration, but they are still needed. And yeah, I will not go into many details, but you should remember that they are important to very specific processes, but that are completely part of the plant functioning. After that, so that these are the needed elements, the essential elements. There are others that are characterized as beneficial elements. It means that they are non-essential, but they can improve the plant health, such as the cobalt, which is needed by the rhizobium bacteria. So it will be required by the leguminous species. You have the silicon. Usually you will find the silicon in form of silicic acid precipitates in the plant. And they have silicon may have a lot of different roles in the plant. Usually it improves the growth, improves the mechanical support of the plant. So when you have straws, the silicon may help to rigidify the stems. And also, it was supposed to have a role in the resistance to fungal disease, or to make the plant a bit disgusting or hard to eat for herbivores and so on. So it can have different roles in the plant. Also, the nickels is recognized now as a beneficial element for the legumes and the small grains, as it could be needed for germination. And then you have the toxic elements. The most toxic or most recognized are the aluminium, which is linked to the soil pH. At low pH, aluminium is under free form, Al3+, and can enter in the plant and provoke disease or malfunctioning in the plant. Sometimes it replaces other elements, or it can have direct toxic effect. And the other one is the copper. Copper is toxic element for a lot of plants, and we have been studying the copper flora in RD Congo, where there are a lot of places that are contaminated by copper, either on natural outcrops of rocks in in the landscape, and you see that you can find a lot of plant species that were adapted to the content of copper in the soil, and other places the soil is completely bare because it's due to human activities, and the plant that are tolerant have not been there yet. And so the idea is to try to use these copper flora in order to vegetize the places that have been contaminated by the plants. And so for a series of plants, the idea is to study their distribution, where they can grow according to the content of copper in the soil. Here you have a scale which goes from 100 milligrams per kilo or ppm in the soil of available copper to 10,000. So at some places there are very huge amounts of copper in the soils, and you have plants that are tolerant to these areas where other plants cannot. And so according to the level of contaminations that you have, you can try to have success with the different kinds of plants in order to re-vegetize this area. So copper is important toxic, potentially toxic elements for the plants. So that was about the characteristics of essentiality or non-essentiality, toxicity. Then you know that plants can have needs, but we also define the plants according to their requirement. They all need phosphorus, for example, but some crops need more than the other one. And so we define requirements for the plants. Usually, you will find table with the phosphorus, potassium, because that's the major nutrient with the nitrogen. But you can also find these tables of requirement for micronutrients. And here, for example, you have a classification of the major crops in Belgium. And we know that sugar beet, for example, is very demanding of phosphorus and potassium. And if you want to have success with this crop, you need to be sure that the soil will be able to give you the demanding the demands of the crop. Also, potato is recognized as a very high demanding crop regarding phosphorus and potassium. Other, such as the cereals, most of them are low required for potassium and middle required for phosphorus. And so, thanks to tens of years of experimentations, you are able to classify the plant into these categories, and you will take that into consideration when you will begin the assessment and the crop rotation or the crop production. The idea is to represent and thanks to define this kind of figure, thanks to the experimental trials in the field, is that you measure the growth. You can have a measure of the growth or the yield of the plant regarding the concentration of the nutrient in the tissue. So you fertilize your soils, and when the element is deficient, it means that if you increase the content of the element in the soils and in the uptake by the plant, the yield will grow. Then you have an adequate zone in which the plant is in good conditions regarding the growth or the yield. And then you have a toxic zone for certain for various elements, not for everyone, but for the elements that are toxic, you have a toxicity threshold that can be defined. So here you are in the deficiency zone, here you are in the sufficiency zone, and here you are in the toxic zone. So it means for the elements and for most of them, you can have symptoms, visible symptoms of deficiency or excess if you are in these extreme zones. For example, for the nitrogen, when you don't have enough nitrogen in the soil, you see that you will have decoloration of the leaf. The older leaves turn yellow and will turn brown and die. Plant growth is slow, and you will be too early maturation. So you will, for most of the crops, you will have a very slow yield. And at the opposite, when you have excess of nitrogen in the soil, you will have the plant will be dark green. You can have insect infestation, drought stress, and so on. Sometimes also you can have I don't know the English name, but it's kind of fall down of the cereals. So if they grew too fast due to the excess of nitrogen, and they are too fragile, and if there's a bit wind or windy climate, they will fall down in the on the soil. Also, so this was for nitrogen, but you can find the same for ammonium. For phosphorus, the plant growth will be slower. You have characteristic purple coloration of the leaves. And when you have excess, it's indirect symptoms. It's symptoms of other elements such as zinc, iron, and manganese that can be deficient if there is too much phosphorus in the soils, because phosphorus will bind to these elements and they will be less available for the plant. Okay, so that was first part. Don't know if I make a stop here to know if there are questions.
Yeah, I think that's a good idea, Gilles. Already, thank you for giving this overview. I saw that Sergius already put in the chat a link to this book that you recommended on plant nutrition and soil fertility manual by Benton Jones. So indeed, this could be additional lecture. I don't see any questions, but maybe I can ask you one, Gilles. At some point, you showed all the nutrients and elements that are needed. Yeah. And for carbon, you were saying this is CO2 from the air. Can you tell something about the role of organic carbon in the soil? Does it also deliver carbon to the plants, or what does the soil organic carbon gives to the plant in the sense of nutrients?
No, organic carbon is not from the soil is not a nutrient for the plant, not at all. It's more, yeah. Sometimes some uptake can be made from chelates, so a combination of mineral elements and organic molecules, but it's not dedicated to really to build the cell walls and so on. Yep. It's really as a nutrient for the plant. This carbon comes from the atmosphere.
Yes. Okay, that's clear. Thanks for pointing this out. I don't see any other question, Gilles, at this moment. So I propose you start your next part on the nutrient behavior in soil.
Okay. So yeah, that was anticipation of your question. You anticipated here. Regarding the organic matter, which is important for the soil, carbon comes from for the plant comes from the photosynthesis. So carbon is uptaken by the plant in the leaves and stored in the above ground biomass, and can be stored in below ground biomass either by the litter, so the leaves and the aerial part when the plant dies goes to the soil, or it's also a big input by the roots when they dig. And all this system is respirated, so the plant sometimes consumes oxygen and liberate CO2, but also the microorganisms which are mineralized, making mineralization, it's very hard to say, mineralization of the organic matter in the soils, and so there is a production of CO2. And there are important fluxes of carbon, and forests were seen as a carbon sink, while the use of agriculture and deforestation was seen as a carbon fluxes to the atmosphere. And if we look at what happens to the organic matter in the soil, there were some models, useful model because relatively simple model to understand and predict the fate of organic matter. One is the Hénin Dupuy model, which was developed in France. They say when you have a quantity of fresh organic matter residues or litter or organic inputs, you put waste, animal waste to the soils and so on. The organic matter will be eaten by the microbes to make their cells, and the residue of this mineralization is the CO2. And the other residue is what is called the stable organic matter in the soil, or the humus. So they distinguish two coefficients. One is the humification coefficient, which is the part of the fresh organic matter that will give you stable humus in the soils. So this is called the K1 coefficient, and 1 minus K1 is the part of the fresh organic matter that will be converted into CO2. And then the stable organic matter is not so stable because it also can be used by the microorganism. And we have another coefficient, which is the K2, which is the proportion of stable organic matter, which is converted into CO2 on an annual basis, usually. It is used like that. So this is the most simple when you want to have an idea of what will be the fate of organic matter in the soil. There are some more sophisticated. Here you have the Rothsey model, so that was developed from the Rodamstedt experiment. When you have organic inputs, one will give you, so they are composed of decomposable material and resistant plant material. And both have their own dynamic of evolution and will give you CO2 or microorganism or stable organic matter. And all these compartments still evolve, and you can define coefficient of mineralization, coefficient of decay, and so on. The only pool that doesn't change into the soil is the inert organic matter. So and there are models that are more sophisticated, but the more you add pools and equations of evolution, the more you need data to make it work. Regarding the the carbon pools in the soils, they are sensitive to agricultural practices. And here you have a study, a study that was made by Tiefenbacher et al. It was a review of the effect of agricultural practices on the carbon sequestration in soils. And compared to bare fallow, which liberates carbon into the soil, there are other practices that can have a positive effect. So it means that there is more carbon in the soil after, such as no tillage, use of catch crops, amending with the compost. Here it's a reduced tillage, deep rooting crops, and so on. So there are kind of practices that are known or supposed being in favor of the carbon sequestration in the soils. The result of the practices will greatly depend on the context. So you should always be careful about the use of these kind of results. So organic matter was not seen as I presented it first, not because it's a nutrient, but because as an organic matter, it is a source of the other nutrient. And so the evolution of organic matter is important. Regarding the nutrient, and here the nitrogen cycle in the soil, the main forms under which the nitrogen can be uptaken by the plant are mineral forms, and it is either nitrate or ammonium. There is, so that's the main for most crops, that's the main sources of nitrogen. And in the soil, the ammonium, the fate of the ammonium is to be either uptaken by the plant or nitrified into nitrate, or to be volatilized into the atmosphere. The sources of ammonium are direct deposition from the atmosphere, can be fertilization, or it can also be the mineralization of the organic matter. So the microbes are eating the labile organic matter, the microbes are eating microbes, and at the end, you have production of ammonium to the soil. The other source of the other source of nitrogen is the nitrate, and nitrate can come from the fertilization or from the nitrification. Nitrification is done by the microorganism in the soil. So there is an oxidation of the ammonium. And regarding the fate, it can also be taken up by the plant or by the microbes, or can be denitrified and go into the atmospheric pool, or it can be leached to the groundwater. As the soil is major with the cationic exchange capacity, the ammonium is not so sensitive to the leaching. And sorry. One other important point is that some plants, such as the legumes, are able to take up the nitrogen directly from the atmosphere and to through the association with the microbes in their roots. So they are able to fix nitrogen in the soil. And sometimes it is viewed as a means of fertilizing the soil, is that you put some legumes, they will enrich the soil, and the crops that will come after will be able to benefit from this nitrogen when the plant is mineralized. So nutrient, the end cycle is important. Also, so there might be potential big issue linked to the end cycle, and one is the sometimes you should be aware that there can be acidification process. The idea is that when you have ammonium in the soil, if the plant uptakes ammonium, the exchange money for the plant is H plus. And so it means that if the plant takes ammonium, it will give H plus into the soil. So there's a risk of acidification. Also, when you have transformation of ammonium into nitrate by the nitrification, it also releases the H plus. And so it can be at the end an excess of proton of H plus into the soil. And it's important to clearly think about what kind of nitrogen form you put into the soil in order to prevent the risks of acidification. Another nutrient, of course, is the phosphorus. And regarding the phosphorus, you also have different forms of phosphorus into the soil. The major source for the plant is the dissolved phosphorus. So it means that the phosphorus must be into the solution before being uptaken by the plant. This pool of soil solution is alimented, comes from either the mineralization of the organic phosphorus, and the organic phosphorus will give you a collection of molecules, of which stabilized and others are called as active phosphorus. And it's mainly the active organic phosphorus with molecules such as orthophosphate diester that can feed the soil solution. And this organic phosphorus is controlled by the activity of the microbes. And the other part of the theme here, you have the inorganic phosphorus, which also have different pools with different solubility. Some are considered as insoluble, such as the apatite. Some forms of phosphorus are linked to calcium, iron, aluminium, phosphate. So these phosphates are precipitated and can be mobilized by the soil solution with the processes of dissolution. And then you have weakly bound phosphorus, which is called salt phosphorus on the clays and metal oxides. And it's processes of sorption, desorption that controls the quantity in the dissolved soil solution. If we look at the stocks, usually at the phosphorus in the total phosphorus in the soil, so the sum of all the pools here is equivalent to 1 to 3 tons of phosphorus per hectare. If you look at the plant need is counted in kilo, not in ton. So it's 20 to 60 kilo of phosphorus per hectare per year. And if you look at the phosphorus, which is in solution, it's a few kilo per hectare. So it means that the plant will take up the phosphorus in the solution, and the solution must be in frequent equilibrium in order to be able to feed this soil solution. Either the plant is able to control the mechanism by modifying the environment of the roots in order to accelerate the desorption or the dissolution of the phosphorus. We look now at the potassium cycle. Potassium is mostly a matter of mineral phases. Again, the uptake must be made through the dissolved potassium in the soil solution. The dissolved potassium can be uptaken or leached, or it can be sorbed on the cationic exchange capacity. And this form, which is sorbed, can also enter through the structures of the minerals, mainly the clay minerals. When when they are weathered, they are opening themselves, and the space between the layers of clay is becoming wider, and the elements that are there can go out. But there is also the reverse processes, is that the potassium comes and begins to force the clays to inside layer to go thinner and kind of fixing the potassium. It is more fixed and it's not available for the plant. So we have processes that must act on the dynamics of the slow release, fast release processes in order to that the plant has enough potassium. Otherwise, the other needs will be taken into consideration by the fertilization process. So, contrary to the phosphorus and the nitrogen, the importance here of the organic phases is really low, and it will be kind of the same picture for the magnesium. There have been some small differences, but globally it's the same picture. It's mostly the mineral pools that are important for the uptake of the plant. If you look at the sulfur cycle, you can find sulfate or sulfide in the soils, but most of the reserve of the sulfur in the soil are organic forms, and these organic forms need to be mineralized into sulfate for the plant being able to take it up. So it's a different topic or different image than the potassium. It's completely the reverse here. Most of the sulfur is under organic form and will go into sulfate form through the activity of the microbes, and then taken up by the plant and assimilated into other organic material in the plant. Usually, we did not matter a lot about sulfur in the soil. It was not really part of the fertilization processes. But now, as there is lower sulfur deposits from the atmosphere, because there were a lot of regulations that limit the emission of sulfur to the atmosphere from the industrial activities. So lower quantities of sulfur deposit on the soils, and now you begin to see some kind of deficiencies in some soils for sensitive crops, and there are no companies that sell gypsum products or other sulfur products to increase the sulfur in the soil. Regarding the fluxes of nutrient in the soil, as for the metals, there are three kinds of movements here in the soil system. So you will have the solid phase here, the plant roots, and the intermediate between two is the soil solution. First, you will have convection processes. So it means that the water is taken up by the roots and the elements follow the flow by convection. The other one is diffusion. So it means that when you have concentrations, here you have higher concentration, here you have lower concentration, and the elements are migrating in order to compensate this gradient of concentration. This is often the case when the roots are taken up the elements. So it means that you provoke a group here. You have less elements, and so when the reserves are the soil solid phase, you have a gradient that might be a mark. So it's really important for the elements that are taken up more intensively by the water uptake than the other one. And the other one is the root displacement. So that's the root that can go and try to find the elements in the soil solid phase. So that's kind of a root scavengering of the soil, and an important, we say plant roots, but important elements that are in the system is the mycorrhiza. When plants can make association with the mycorrhiza, it increases a lot the capacity of the soil to forage the roots to forage the soils and to be able to mobilize elements that cannot be that cannot follow the water fluxes or the diffusion gradient. So maybe I make another stop and then we go to the management schemes.
Okay, that's good, Gilles. Thanks once again. It's indeed interesting to see how all the interactions take place and what the role is. There is no question in the chat at this moment. Let me just look around. No.
Okay.
No, I think it was clear, Gilles. So please proceed with the following part.
Okay. So regarding the schemes of soil fertility assessment, I told that the FAO schemes exist for many years, and even if it has evolved, the idea at the beginning was that regarding really the soil parameters, you could define some limitations. So you have a classification of the soils according to the number of limitation and the types of limitations that you can find, such as a soil has erosion risk or excess water, or some rhizosphere limitations such as pore structure, pore permeability, pore chemical status, poor biological activity, risk of salinity or contamination. There were a parameter which was the quantity of available water for the plant, or the depth of the soils, the stoniness, the slope, and so on. So that was kind of identifying risks, limitations for the crops. In the USDA, they developed something really similar, which is the land capability schemes. And in this land capability, you have 8 classes according to the limitations for the crop. Class 1 is slight limitations, then you have moderate limitations, severe, very severe, and so on. So different kind of limitations that are recognized, and then you have subclasses which define the type of limitation, such as erosion risk, soil water storage, salinity, and so on. So this is, if we look now at really the chemical nutrient status, usually it should be based on response of the crop to rates of nutrient in the soils. And so there were a lot of trials, field trials, where you put some, for example, nitrogen fertilizers with 80, 100, and so on kilos per hectare, and you see is there an increase of the yield. And when you are at the plateau, you know that you can have the appropriate number of kilos per of nitrogen per hectare. You don't need to go further. So regarding the so the idea is to make trials and see by the trials if you need to put some additional elements. So that's the what's called the fertilization, and the fertilization follows what are called the classical laws of fertilization. The first one is the law of minimum or most limiting factor, which is also called the Liebig law of fertilization. It can be often represented as a barrel here. With it means that the yield that you can expect will be controlled by the lowest limitation, or the most limiting factor. So you can here suppose that you have a soil which has good levels in carbon, nitrogen, phosphorus, sulfur, and so on. But the selenium is a limiting factor, and it will impeach the good yield. And so if you want to increase the yield, you first have to control these levels. And if you want the maximum yield, you have to alleviate all the limiting factors. So this is first law of fertilization, which is Liebig law. The second one is the law of diminishing return, so-called Mitscherlich law. It means that when you are putting fertilizers on the soils, you will have an answer with the increase of the yield. So this goes as the most productive part. So you have a big increase of yield when you put some fertilization. Then you have kind of maximum, and it is called as diminishing returns. And then you can have a decrease of yield. And so the benefits of the fertilization tends to decrease with the amounts that you are going to put. So that's the law of diminishing marginal returns. And when you are here, it's not worth to put some additional fertilizers because you will not have a bigger yield and you will only waste money. Third law is that in the fertilization is that is called the law of the restitution. So it means that when you make assessment, what you put into the soil plant system should compensate the fluxes out of the system. And so you must compensate the export by the plant. You must compensate the leaching out of the soil. You must compensate eventually the erosion. So elements are leached but by the surface. And also, so in some cases, you can compensate the fixation into the soil, such as the potassium, which is a part of the potassium that you bring as fertilizers, will be blocked by the clay. Okay. So that's the third law of fertilization. What you bring should compensate what is going out of the system. And so usually this law is used by the practitioner in order to define the quantities of fertilizers or amending matter that you should put into the soils. You define the crop and you define the target of yield. You define the crop demand. So it means that some, as we saw, the sugar beet, for example, might have a high demand of phosphorus and potassium. You define what the soil can offer. The crop rotation means that maybe before your crop there was a legume that will leave some nitrogen in the soil and so on. And so you can define your fertilization as first a compensation of the losses by exportation and the losses in the system, and an addition to the soil offer in order to define your target of fertilization. And this is mainly based on the soil analysis, but also you can use the plant analysis to see if your crop need something. So there are two major ways of defining the needs of fertilization. One is based on the soil analysis, and the other one on the plant analysis, and they can have a mutual benefit. Maybe one does not exclude the other one. So the main idea when you will assess the state of the soil is to be able first to evaluate if it's in a good state, or if you can identify some weaknesses, for example, phosphorus deficiency, risk of phosphorus deficiency, of potassium, and so on. The general idea is to give the crop what it needs according to the expected yield. And if you have weaknesses, to correct the soil properties, such as the pH, the nutrient status, in order to be in a good state. And when it's in good state, you give the crop what it needs. And you don't really take into consideration the other characteristics of the soil, such as the soil types and so on. So that's something that has been long used by the agronomists. They did not really recognize the soil types. They just say, okay, the soil is a support for the plant, and we give the plant what it needs, and we can correct some chemical part of the source when it's very obvious. Here, if you want to make the state of evaluate the state of the soils, you can take the soil type into consideration when you know it, and you can have reference values that are recognize the type of soils. For example, you could have different reference value for soils with Louvi soils or for Chernozem and so on. Sometimes you also have reference value for interpreting your data that are linked to soil texture. We say, okay, if we have clay soil, we will need to have to consider this value as high or low and so on. And it will be different kind of threshold if you have a sandy soils or a loamy soils. So the idea is to measure the soil properties and try to refer to reference values that might be the soil types, that might be that might be the soil types, that might be the soil texture, or that are considered as more universal, such as the pH scale. You know, it's basic, it's neutral, it's acidic, whatever the soil type. You need to have usually levels to interpret the data. Here it's a table that I found for Ukrainian. So there are agrochemical indicators of soil fertility. And so classification of pH, of P2O5, of K2O, and so on, with average high, average low, and so on. So there are standards in Ukraine. I don't know them. If you have this classification system, I would be interested to have it. But yeah, it means that there is systems in usually every country can refer to local references. So regarding the parameters that we'll take into consideration, as I thought, if you have soil type, it's okay. If you don't, at least knowing the soil texture might be important because it's a driver of a lot of soil functioning. The water of water availability, for example, is dependent on the clay, but also the capacity of the soil to fix various kind of nutrients is also linked to the clay content, for example, and the nature of the clay. And so your interpretation may differ according to the clay content. The tool that is used is usually the triangle of texture. There exist different kinds. Yeah, I think it's the one from the FAO. We have our one triangle for a Belgian system. There is another triangle for the USDA and so on. Also important is to recognize the limits. In our system, the limit of the clay is cut at 2 micron. I think in the Ukrainian system, it's 1 micron. So we can have differences in that system. But the important is to have built its own local of references. Here, we made the first analysis of the Ukrainian soils that we have, and we know that looking at the various results that we already have, we have 4 groups of texture. One is in silty clay loam, one is on clay loam, one is on loam, one will be in silt loam. So they should have different kind of functioning in the field, and maybe the interpretation system that you need will depend on the type of soil texture that you have, and you should treat them differently. So that's the texture that will give you indication of, about maybe the nature of the soil and the importance of the clay content. Another parameters that give you also the frame. It's the soil cationic exchange capacity. We usually make an image with a fridge. It's considered as the fridge of the soil. So it's the quantity that the soil can store of nutrient, of cationic nutrient. So the soil cationic exchange capacity is a measure of the soil capacity to sorb the cation by electrostatic forces. So when the elements such as the calcium is in the soil solution, it is surrounded by molecules of water, and they constitute the outer sphere complex, which at the H plus here at the border gives a kind of positive electronic charge, and the soil dominantly presents negative charge due to the dissociation of the border complex, or due to substitution of elements in the internal clay layers. So aluminium is 3 plus and can be replaced by iron or magnesium, which is 2 plus. And so there is a deficit of positive charge that creates a negative charge. So the whole structure here has globally negative charge on which the cation can be temporarily sorbed. So this is generally the image of the fridge. You can have a small fridge, small CC, or you can have a large fridge, large CC. The largest it is, the more nutrient you can store, and the smallest one, of course, the smallest quantity of nutrients you can store. Sometimes it can be sufficient to have a small one if the dynamic of putting nutrients in the fridge is high. So sometimes it's better to have a small fridge and always elements in it, rather than a big empty fridge. Why it's important is because this size of the fridge in our system and in other system of classification of the nutrient status, the interpretation is based on the ideal cation occupation. So it means that if you have a fridge, it should have 60% of calcium, 12% of magnesium, and 10 of potassium, for example. So you can decide this. So that's the physical, it's the texture, it's the cationic exchange capacity, and of course after you have the soil reaction, and the most widely indicator of soil reaction is the pH. So the pH is a measure of the soil activity of H plus in the soil solution. And pH is very important because it will influence many processes in the soil, such as the availability of the elements, the size of the fridge, and the physical sorption. Usually, we measure pH by mixing the soil with water, and you have water extractable acidity, and so you measure the activity of the protons in the soil solution. But you can also, and it's more, it's a parameter which is more stable through time, is to measure a part of the exchangeable acidity. So it's the acidity which is linked to the surface of the clay and the humus that are attracted by the properties of the colloid. And what to to evaluate this, you replace the water by a salt. And usually we use KCl, but some other references are based on other salts such as CaCl2 or BaCl2 and so on. And so with the KCl, you displace some of the protons here to the soil solution by replacing them by potassium. And then after, there's still another kind of acidity, which is more bound onto the clay and the humus, and that you don't measure with the classical extraction. So this is also widely used figures about the effect of soil pH on the plant nutrient availability. And so considering that the best area of availability for most of the plant is between 6.7 and 6.5 and 7.5, it's where you have the best optimum available element, nitrogen, phosphorus. If you are in too acidic conditions, these elements won't be available. You could also have higher availability of iron and metals, and that could be a problem if they are in too high concentrations in the soils. And if you are under alkaline conditions, you also have risks of deficiencies for the metals, for the micronutrients, for example. So there is a good range of conditions to try to present for the plant nutrient availability, which is between 6.5 and 7.5. Regarding the nutrient status, so that's the table of classification that we have. So sorry, there is French in it, but globally in our system, we recognize either texture, such as sandy, silty, or clayey, or cationic exchange capacity. Usually in sandy soils, the cationic exchange capacity is lower, so we have less than 5 or less than 10. The silty are between 10 and 15 or 15 and 20, and more than 20 centimoles per kilogram. You have clay soils. And for each CEC level, we consider that the ideal balance of cation is 60, 20, 10% for Ca, Mg, and Nk. And so this is the ideal balance. And with that, you can calculate, multiply by the CEC, and you have approximate levels. If you are good, it means that you are on this balance. If you have more calcium, you will have high level or very high level, or low level or very low level. So this is an expression of the distance that you have with this ideal balance, and you will add fertilizers usually when you have on low, very low status of your element. Another point to take into consideration is that that's the level of elements, but for some elements you can have interactions and antagonism. And usually it's for for potassium and magnesium. We consider that there is an optimum range of K2O over MgO ratio. for some of the plants, and the grasslands are typically sensitive to that. And if you have too much potassium, you have a risk of manganese deficiency. And if you have too much magnesium, you have a risk of potassium deficiencies in your plant. So it's not only the levels, it's also the equilibrium between the elements that might be important. And there are others interaction that are reported in the literature, such as synergisms, zero interaction, or antagonism. So this is a study that was published here in 2015. There are probably many others, but it gives you indications about the number of studies where they found what kind of interaction. So when it's green and blue, it means that they globally synergies between the elements, and when it's red, it means that there is antagonism. You can see that sometimes it's a bit complicated. If you look at potassium and nitrogen, all the studies they found were showed that there was synergism. If you look at nitrogen and iron, you see that they had 3 studies. One is green, one is orange, and one is red. So it's a bit difficult to make conclusion about that. So for calcium, magnesium, potassium, we have an evaluation scheme based on ideal cationic balance. Regarding the phosphorus, it's a bit different. We have we recognize the importance of the texture. So light texture is sandy soil, medium texture is silty soils, heavy texture is clay soils. And also the pH is taken into consideration. And regarding these 2 elements, we have threshold, low, medium, and high. And what is called here valeur pivot in French, it's the threshold under which you consider that you need to put fertilizers, more fertilizer. The level is too low in the soil, and over which you don't do anything. The trend usually in the more recent fertilization philosophy is that you defined levels according to the requirement of the crop. If you have a non-demanding crops, you will have a threshold under which you should fertilize and over which you just stand still. You don't do additional inputs. And for demanding crops, of course, this threshold will be higher. So usually the system of fertilization now, so in systems such as the one used in France, recognize 2 levels, one for non-demanding crops and the other one for demanding crops. This is for now nitrogen. Usually, you have a balance between the needs of the plant and globally, you define the quantity of fertilizers that you will put according to what can be brought by different sources in the soil. In the worst case, you just say, okay, I will make this quantity of sugar beet per hectare, and the demand for sugar beet is 100 kilo. It's an example, 100 kilo of nitrogen per hectare, and I give 100 kilo. In more sophisticated models, you have different modules that calculate what can be already present in the soils, and you should take that out of the quantity of fertilizers that you will bring. The fertilizers, nitrogen in the soils, sorry, can be put into the system by symbiotic fixation if you have legumes, by irrigation inputs if you irrigate, by the previous crops if you left some crop residues in the soils, by the organic inputs if you put manure, for example, by the mineralization of the soil organic matter, by intermediate crops. Here in southern Belgium, you cannot leave the soil bare during the winter, and you are encouraged to put intermediate crops that will prevent the leaching of a nitrate to the. But when you put that crop, when you destroy it, you just incorporate it into the soil, and it can give you some more nitrogen. And also, you can have a measure of the nitrogen, which is already in the soils at the end of the winter before you make your fertilization of the crop. And there's a calculation. There exist some tools online. This is an example of. It's in French, but yeah. This is an example that we can find, and probably it exists in English somewhere.
Gilles, we don't see we only see a black screen at the moment.
Okay, yeah. It's because I shared I shared the other one. I will share this one. I'm sorry. Yeah. Do you see it?
I see it only on the top. There is a yeah. Can you even get it smaller now? But we see most of it.
Yeah,
I think. Yeah. I think that's working. Okay, that's good.
Yeah, that's the system here that was developed by an agency which protects the quality of the water. And you just say, okay, I want to grow a sugar beet. And so it calculates the needs. Its sugar beet needs 240 kilo of nitrogen per hectare. And so you will say, okay, my pH is a little bit more acidic. And he will tell you that you in the system, you will have 30 kilos which of nitrogen from the source, which will not be taken by the crop. And so the quantity of nitrogen that is really needed is not 240, it's 290, because you have 240 plus 20 kilos here due to the acidity, and 30 kilos, but because we know that the plant will not be able to take all that we will bring. And so this is your needs. After you will have to say, okay, which quantity of nitrogen I have at the end of the winter. Okay. In my case, I say, okay, I have 50 kilograms, which is still in the soil. I have a small quantity of organic matter. I never put manure. Before I had a wheat, and this is the quantity of organic matter that I put. So there's no zero, and I did not put any intermediate crops. So at the end, I have the quantity of nitrogen that can be bring by the soil. So it's 100 kilo. It needs 290 kilo. So the difference is what I need to bring to the soil is 188 kilograms of nitrogen per hectare. So that's the kind of tools that are rather easy to manipulate. So I will go back to the presentation. Okay, you away this, I suppose. Maybe finally is the a way to improve and to keep living soils, to keep a soil that is just not just physical support of fertility, is to try to work to the organic matter levels, because organic matter is very important roles into the chemical properties, the biological properties, and the physical properties. So it should be a real key to sustainable fertility levels of the soil. I don't know why this one don't want to go away, but yeah. Also, I did not speak about micronutrients, mostly because you seldom put directly micronutrients and in the as a fertilizers, such as you could do with the nitrogen, or you could do with PK, for example, because all the fertilizers have a cost that may be prohibitive. And so for micronutrients, usually you wait until you have a diagnostic of the leaves that tells you that you have deficiencies, such as here a photo of a deficiency in the maize leaves. So it tells you that you miss some elements, and then after, I think it was for zinc. Usually, you correct the deficiencies by applying local. Usually, it's foliar applications of the micronutrients such as zinc or iron and something. But yeah, as all as a cost, you should not waste your money if you don't need to put micronutrients in the soil. I think that's close to the end of the presentation. Is that with the fertility assessment, it's important to be able to make regional assessment. And so that's also like that we built our reference value. We have gathered, for many years, we have gathered the results of analysis by the various laboratory that work. We have one laboratory in every province that is making analysis for the agriculture, for the farmers, and they are all in a network in which we work, and they all gathered the results of the analysis into one centralized database, and we can use this database. Here is an example of mapping of the Walloon region for the phosphorus for the crop soils, and here phosphorus for the grassland. So we see that there are differences of levels. And it helps us to have a good idea of what is the mean level of available nutrients. So we have it for major nutrients for pH. And also it can help us to have now an idea of the evolution in the time, because the first database was built at the end of the 90s. And so we have now a lot of data. Don't remember exactly the right number, but it was more than 400,000 results of farmers that were in the database. And so we can see if for some region you have trends. We see that the carbon is going down at some places. We see that phosphorus is also going down at some places. So magnesium is rising at other places. And so we can have general idea, and we have a good reference system to say, okay, this level is low, this level is high for the Walloon region. So if I conclude, the ideal soil for growing crops should have loamy texture for ease of air and water movement in soils, but that's something that you cannot manage. You cannot change the texture of the soils. So regarding what you can manage, you have organic matter content sufficient to maintain the other properties and a good biological activity. No physical constraints and large volume available for roots. Good size of bridge. No presence of elements at potentially toxic levels. And really what you can do is balance nutrient status, allowing growth of most crops and fertilization plan to adjust the nutrient availability to plant needs for demanding crops. So that's the main philosophy. You put the soils into good status, and if plants requirements are high, you just complement that. Thank you for your attention.
Okay, thank you, Gilles, very much. I know that soil fertility is a science on its own, so I can imagine how difficult it was to put it in one session. But I think you highlighted the most important parts of what affects soil fertility. You also said something about soil health in general, what are the processes and why it's so important. For us, it was really important to have this session in the training program as well, considering we are talking about agricultural land. So besides the contamination, of course, also what micronutrients can do and how everything is working together in a process is also really needed to understand the full. So I think, yeah, I got only a positive, no question, Gilles, but a comment. Thank you. This information was interesting and clear. So I think this summarizes it, it well. Just have one more minute just to see if there is anything else from it. yeah, I think as you have shown, there are a lot of tools available in different countries on how to deal with it. I can imagine also in Ukraine, different tools are available. So, but it's always good to keep in the back of our mind all these processes. Okay, I don't see it at the moment, Chill. Once again, if you still have questions or comments, they can be sent to us later on. So if everything is well, we have now a 2-hour break. And in the afternoon, so within 2 hours, we will see each other for the first session on the polycyclic aromatic hydrocarbons. So it will be more related to analytical techniques. So we will shift a little bit to that environment. So, but first, I wish you all a good lunch, and then we see each other within 2 hours. And Gilles, thank you once again for this really nice presentation.